All right, now we can keep on going. There are other interesting results that we can see from this. For example, the hyperbola. Now, we've seen the hyperbola before and noticed that it gives us some weird things, like when we looked at inequalities. It was strange, right? What is this going to tell us about the hyperbola? Well, for starters, I suppose since we're differentiating powers of x, right? We ought to phrase this as a power of x. What is 1 on x? As an x. Good. It's the derivative of that is the derivative of this. Okay? Please don't leave off your derivative there and just say it's equal to that, because it's the derivative of this. So it's the derivative of this. Does that make sense? Okay, so here is the first thing when you differentiate a constant. Now we differentiate the hyperbola. Okay? Let's see what happens. Look at the rule. Look at how we used it before. This power is going to come out the front, right? So I'm going to slap a minus sign here. Okay. And then the power up here should reduce by 1, right? N minus 1. Now it's currently negative 1. So if I take away 1 from that, it'll become negative 2. Do you agree with that? Now this is a bit weird. Let's go back to our, get rid of our negative indices and that kind of thing. This is minus 1 over x squared. Okay. Now, you ought to be suspicious of this a little bit, because just think about how we developed this rule. Think about how we developed it. What did we do? Yes?
Because like when we started it, the powers were going down as you differentiated, but when you did that, it went up. Like the power.
Yeah, okay, alright. So to pull you back to where our heads had to go to develop this, right? I relied on a particular result. I relied on this result. Actually, I don't need that. That will do. What did I have? I had this, right? Because I had to do... Sorry, no, that's not what I had. Oh, yeah, I kind of had. I had to do this. Do you remember this? Do you remember why I had to do this, right? I was putting this guy, right, through the first principles thing, right? So this is f of x plus h. You remember that, right? And then I had a factorization for this. Same, opposite, x to the n minus 1 h, and on and on and on and on. Do you remember this? Yeah. And then I had all of these terms on and on and on, and then I expanded out and I did some cool algebraic tricks, okay? But if I pull this same thing over here for this, what happens to my pattern? Yeah.
Would it be easier to explain it as x minus h, because everything would be y?
It would be, either would be the same. Either would be the same.
Yeah.
You'd get the same result, just without a minus 1. What is this? This is this, isn't it? Yeah? So it's like, am I getting the same expansion? Something different seems to be happening. Like I don't have this kind of thing, right? So you should pose the question, like, can I just take advantage of this pattern I noticed before, which just had to do with positive numbers, right? And does it necessarily keep working when you throw in a spanner like that, okay? Now we have 2 tools at our disposal. We have 2 tools, and we're going to use both of them, okay? The first tool is, just look back on the board, right? What is this thing supposed to be? It's meant to be the gradient, isn't it? Like we've worked out the derivative, but the point of the derivative is that it gives you the gradient, okay? So we know what 1 on x, what it looks like, so we ought to be able to think about what its gradient looks like, right? So draw me a couple of sets of axes, some small ones. We only need to draw 1 over x on here. And draw them one underneath the other, because we're going to make some comparisons here. There's 1 over x. We're very, very familiar with 1 over x. Minus 1 over x squared, not so familiar, but that doesn't make it hard to graph. What kind of things is this thing doing? Number 1, it's even symmetry because there's an even power, right? So I really only need to graph 1/2 of this, and then I'll get the other half by reflecting. Secondly, there are some asymptotes on this thing, right? I can think of 2. What's the easiest one that you can see? X equals, don't just say 0, say I've got a vertical asymptote of x equals 0, right? Because I've got 0, x on the denominator. So I've got a vertical asymptote right on the y-axis, okay? And then I have another asymptote, is it horizontal or oblique? It's going to be horizontal because the degree of the bottom is rather larger than the degree of the top, right? 0 versus 2, okay? So therefore, I've got horizontal asymptote at, and you can fairly easily see, it's going to be y equals 0. Okay, so you've noticed it's even symmetry. I've got a couple of asymptotes, right? What else can you tell me about this graph? If you were to do regions, for example, what would the regions tell you? It's always going to be negative, right? It must always be negative. You can think about it two ways. Number one, you can think, okay, this is a factor, -1, down here, right? This is also a factor, it's always positive. A negative and a positive are always going to multiply or divide together to give you a negative, right? Or of course you can just think, well, this thing is always going to be positive, so when you divide a negative number by that, you'll always remain negative. So I'm going to be down here. Yep. What else can you tell me? Do you need to tell me anything else? Yeah.
It's 1 over a parabola, which means that you basically flip it inside out. So the parabola inside out.
Yeah, kind of. Okay. So if you imagine a parabola here, right? A parabola in here.
Upside down.
Okay. Oh, yeah, sorry, it's upside down. Right. So if I divide by a really negative number down here, okay, a really huge negative number, then I'm going to be -1 over a really huge negative number. So it'll be very small, right? Which is why, as you told me before, I have this, I should have labeled y equals 0 horizontal asymptote, right? And then as I approach over here, that upside down parabola is becoming closer and closer to 0, right? So therefore, when you divide by something closer and closer to 0, you race off to negative infinity. There's half of the graph. Here's the other, because you told me right at the beginning, even symmetry. Okay, yeah.
But it's not going to be like the same points as the one on x, is it?
Correct, because it's x squared. That's right. So what that really means is it's actually going to be steeper, but the general shape is all we need for now. Now let's have a look. Here's my gradient function. Is this an accurate reflection of our original hyperbola? Let's have a think about its gradient. For example, over here. Okay, I'm going to put the signs on like I did before. Okay. Is this gradient over on this side, is it negative or positive? It's negative, isn't it? Because it's decreasing. Okay? So this is right. This is negative down here. What about after we pass x equals 0? It's still decreasing, isn't it? Negative. So far so good. Okay? But it's more than just negative, isn't it? Right? It's not like a straight line, for instance. What is this telling us about the gradient over here? It's for example, over here, it's negative, but it's quite close to 0, isn't it? Right? When a gradient is close to 0, what does that tell you about the line?
Straight line.
It's almost straight.
It's almost straight. It's kind of like this situation. I suppose the way I could say it is because it's not actually straight. It's shallow, which sure enough, it's shallow here. It's decreasing, but not very much. Okay. Now, as you move closer and closer to x equals 0, what's happening? Your gradient's dropping off like a rock. What does that mean? It's getting super steep over here, right? As you get closer and closer, as it should, because it's an asymptote, right? Okay, and then what's happening over here? Well, exactly the reverse, right? It starts off really negative, the gradient, okay? Which means what?
It's really steep.
It's super steep, and then it shallows out, just like you'd expect, okay? So, visually, it looks like it checks out, right? Looks like it checks out. The only problem with doing things visually is that your eyes can be very deceiving. For example, if I hold out, do it like this. No, I'm not going to do it like that. Put it back together. If I hold out this lanyard, right, and I do something like this, okay? Now I know there's two lines there, but just imagine they're one. Now this shape looks kind of like a parabola, doesn't it? It looks parabolic, sort of, doesn't it? Except it's not. It's not a parabola at all. It looks like one, but it's not. It's a completely different shape. It's called a, I don't even know how this is properly pronounced, catenary, I think, right? You can go look it up, right? All hanging chains or strings do this when they're hanging under their own weight. Looks like a parabola, but it's not. This so far looks like it checks out, but how can you really know? Like, this is a pretty blunt tool, right? Yeah.
Because, like, you know, like, I'm just saying a floor in it. You know the bottom one on the right?
Yep.
The fourth quadrant?
Yep.
That could still exist in the first quadrant. Because the gradient would still be right. Wouldn't it?
Hold on, you lost me.
If you pick that one up.
Yep.
and it was in the first quadrant. Wouldn't it still match?
You mean put this up here?
Yeah, wouldn't it still match the gradient of the pitch?
Gradient's never positive.
No, it wouldn't.
It's always
Yeah, because it's decreasing. It's decreasing.
Gradient
So it's
is
got to stay down there. It must absolutely be negative. A way of thinking about this is everywhere that this graph is defined, which is everywhere except for x equals 0, it's always, every point is going down. Every point is going down. They're going down at different rates, but it has to be, it's got to be negative. It's got to be under there. The gradient function has to be negative. Yeah, right.
test points for scale.
Okay, you could test points for scale. That would work. You'd say like here and here, and you could actually draw in some like some secants and see what's going on. Okay, that would work. Except the problem with that is that they're still secants, aren't they? Okay, and so they're still going to be approximate, right? We have a better tool for this. We have a precise tool.
Limits.
No, the first principle
We're going to go back to first principles.
was negative and